Well,
Go ahead.
very good. Good morning, ladies and gentlemen. And this is our first of our wiki of our must series this fall. So today's speaker is my graduate student David Hall, and together with David, we've been trying to use a very simplified one-band model and some very simplistic approximations to try to ask a question: what is the statistics of local charge transfers in electrostatic fields? And can we understand some of the trends that were observed previously in our recent work with Maria, which were published already? But there are a number of questions that we can address. What is the controlling the widths of the distributions? What is controlling the various parameters describing those distributions? And I think within the simplistic model and within linear response theory, we can answer this question. So there we will describe what we have done. It was mostly his work that was accomplished without that much of my help. But so I should really give him credit. He figured out a few tricky things, which is very nice. But after we are done with this, perhaps not today, but maybe another day, I think we'll need to talk about how we can kind of correlate these ideas with DFT work and implement this to better understand the results of DFT modeling that we have done before and pushing forward to describe realistic alloys. So I think without further ado, I think now it's time for David to describe the work that we have been doing for a little while, and then we can have a discussion about what are the next steps. So David, the floor is yours.
All right. Okay, thank you, Vlad. And hi, everyone, and thanks for coming to my talk. So today we're going to be discussing some of our work investigating the charge transfer and the electrostatic Madelung field statistics in disordered metals. And so this is going to include the high entropy alloys that have become quite popular over the past few decades or so. All right. So just to start off kind of broadly, though, let me first introduce the concept of disorder in solids. So see, unlike in periodically ordered solids, where we've got some regular crystalline arrangement of atoms, in disordered matter, there's generally some degree of randomness, whether it be structural, like in this kind of amorphous example here, or chemical, where the atoms are randomly distributed across a crystalline structure. We can also have some combination of the two. For example, I might imagine taking that crystal with pure chemical disorder, removing that center ion there, and then having that vacancy reduce some of the local integrity of the crystal structure. All right. Now, why is disordered matter useful to us? Well, they include the various alloys and ceramics that have served and continue to serve various useful roles in our technology. So from ancient currency, weaponry, and pottery to modern steel infrastructure and aluminum alloy airplane components, these disordered materials have found their way into our daily lives thanks to some of their useful properties, which can include things like enhanced strength or hardness or resistance to different mechanical or thermochemical forms of degradation. All right, so these examples all cover from around the Bronze Age to 2023. So what's next? Well, for that, we can start talking about high entropy alloys, which represent a new class of disordered matter, and whose development marks a recent milestone in materials research and engineering. So what are these high entropy alloys? Well, like I said, the field is still pretty new, so some people may have some slightly different definitions. But in general, the term is used to describe metallic alloys comprising a mixture of at least 4 or 5 constituent elements, all of them appearing in roughly comparable concentrations. And it is both the diversity and the relative abundance of these principal elements that contribute towards some of the remarkable properties that these high entropy alloys have shown over the past 20 years or so they've been around. So some high entropy alloys, for example, have outperformed other conventional alloys in terms of things like material strength or resilience to high pressure and temperature conditions, as well as resistance to things like corrosion or radiation damage. In other examples, these materials have also been shown to have some pretty novel electromagnetic properties as well. For instance, superconductivity and other less conventional forms of magnetism. As another example, I think I've also heard on Taiwanese news channels that they've made some high entropy alloys with more stable electromagnetic resonance. And people eventually want to be using these things in like 5G and 6G antennas and such. So these high entropy alloys, have gained a pretty serious following in the past couple of decades, with a lot of research motivated to, understand how they work, first of all, and how we can tune or enhance some of their properties by playing around with their structure or chemistry and use these in commercial applications. All this being in hopes of, developing the next generation of materials and technology. So if anyone's interested, there's a small graphic here with a few possible applications for high entropy alloys and technology. But that's just a general motivation, right? So what's also special about these alloys is that, it's also their rich composition of principal elements that help stabilize their solid phase, often into a nice crystalline configuration, like what's schematically shown here with the square lattice. All right, so what do I mean by this? Well, as a refresher, let me just remind everyone that, the stability of a mixture is generally determined by the Gibbs free energy of mixing, delta G mix. So if I have, some state variables to describe the problem before and then after the mixing, I can compare the initial state of pure elements to the final mixed product, as I do in this delta G mix, which equals, some G final minus G initial. Now, this free energy of mixing can also be written in terms of a mixing enthalpy term, delta H mix, as well as a mixing entropy term, T delta S mix. And it's precisely the competition between these two terms that dictate the overall stability of the mixed product. So for visual aid, I just pulled a graphic off of Cambridge for a binary mixture between two species A and B, since the same general mixing principles in thermodynamics should still apply. And from this, we can see that with increasing temperatures, the free energy mixing, delta G mix, it generally decreases and becomes more stable thanks to the minus sign that we have out front here. Similarly, if I increase delta S mix, well, then I can entropically stabilize the solid solution instead of using temperature T as my driver. And this is basically the mechanism behind the formation of stable high entropy alloys. Because, since we have so many elements with comparable concentrations to choose from, that means there are many possible global configurations that we can create, such that the configurational entropy term, T delta S mix, can dominate and then lower the mixing energy to stabilize the solid solution. And again, when the high entropy stabilizes the solid, well, we can often end up with a single crystal alloy of pure chemical disorder, like we have here. So while we're here, something I also want to point out is that, going back to this particular binary example, we do see here that they included this camel hump feature, which develops as, the enthalpy delta H mix starts to play a bigger role at intermediate and lower temperatures. So notice that, this hump sits right between these two free energy minimum here, or these two here at intermediate temperatures. And then across this region, we have the so-called miscibility gap, where the solid solution can dissociate into two stable phases corresponding to these two free energy minima. Now, similar multi-phase physics is definitely relevant for high entropy alloys, especially when we're talking about things like graining or microstructure of the alloy and mechanical strengthening, right? But before we can even think about multiple phases, we should at least develop a more complete understanding of the single phase physics, right? So for that reason, today we're going to mainly be focusing on the single crystal phase in high entropy alloys, which is just a problem that's controlled by chemical disorder, like what's shown over here. Also, if anyone's wondering, wait, what about structural disorder? Well, this also warrants some attention. However, if I take the chemically disordered lattice that I have over here and then introduce a small vacancy like I did on the last slide, well, we already saw that, this distortion is a pretty local perturbation on top of an already established crystal structure, which remains, pretty square away from the vacancy, in this example at least. So what that means is, we should still try to understand the single crystal problem before we start perturbing it with structural defects. And sure, if we add many defects, eventually the entire crystal will collapse, and then we'll have to worry about the amorphous phases as well. However, this is outside the scope of our work today, and I'll just mention that, there's already another field dedicated towards the study of high entropy amorphous alloys specifically. So we'll put structural disorder off to the side for now, and just reemphasize that for the remainder of our work, we'll be focusing primarily on this problem of pure chemical disorder. Right, so we'll get rid of that and focus on the high entropy alloys single crystalline phase. All right, so now we have some idea of the problem that we want to study and the motivation to study it. So let's talk a little bit about what the general tools and methods are available today for treating the disorder problem that we've just described. So as a bit of background, you're all probably familiar with density functional theory, DFT, which provides popular and well-established methods for self-consistently determining the electronic band structure and properties of many conventional periodic solids. So this is usually accomplished by solving an effective single particle Schrodinger equation, either directly or by proxy using a Green's function, like in the Karinga-Kahn-Rosker KKR approach. Unfortunately, though, applying such methods naively to the chemical disorder problem can present quite the implementation issues. So see, for disordered solids, we can just exploit the precise crystal translational invariance of the problem, and then consider, just a single or maybe a few unit cells of the lattice. For the disordered problem, however, we have to capture randomness over larger length scales if we want to properly and accurately account for the statistical nature of the random solid. All right, so conventional DFT methods, therefore, become prohibitively expensive as we try to treat these massively disordered supercells. Now, these implementation issues aren't exactly new, though, and people have had some time to think about things and make various efforts in recent decades to try and circumvent such issues. And today, there are a number of options available for realistic modeling of disorder, made at various levels of approximation, accuracy, and computational affordability. Of these, the first that we'll mention is the effective medium approach that follows the coherent potential approximation, or CPA. And traditionally, under this framework, the problem is solved by mapping each atomic species over to a uniform medium that represents the species' average environment in the random crystal. So I'd, for instance, pick out this blue atom in the center here, embed it into an effective medium, and then I solve the single-site DFT problem, where this lighter checkerboard pattern might correspond to the electron density produced in the DFT step. So clearly, the single-site mapping makes the problem much more simple conceptually and makes things much more computationally manageable as well. There is a trade-off, however, in that the CPA problem discards the disorder-associated statistics and fails to distinguish some important features in the local chemical environment. So what I mean by this is, I can take the electron density that I just computed in the DFT step, map it back onto the lattice, and then to fill up the rest of the crystal, well, I just follow the same exact procedure, right? Maybe I'll pick out this green atom now, embed it, and then solve the DFT problem once again. But what do I notice here? I notice that the green atom sees the same exact CPA medium that the blue atom did, because each atom in that crystal sees the same environment on average. This turns out to be a pretty questionable approximation to make, which can limit the accuracy of the CPA solution and its ability to properly describe the disordered solid. Moreover, this effective medium approach ends up wiping out the statistics of the problem, since the single-site DFT only depends on what kind of atom is being embedded. So, even if I'm looking at two green atoms that actually have completely different environments due to the disorder, I'm not capturing that CPA. Instead, if I just finish treating out the rest of the crystal, pretty soon I'll end up with something like this. So every green spot is the same, every orange spot's the same, every blue spot's the same. And this is a problem for us because, we know that these atoms actually have different chemical environments thanks to the disorder, and that there should be some statistics associated with this, which a more precise DFT treatment should be able to capture. So in this manner, the CPA solution tends to miss out on some important information about each atom's distinct chemical identity and overlooks, the statistical nature of the disorder problem. With that, I'll just mention another approach of the problem, which may capture this chemical disorder a bit more appropriately. So this is known as the locally self-consistent multiple scattering, or LSMS method. And with it, we can actually treat larger supercells, by establishing some radial cutoff, and then including them during a locally self-consistent DFT step, LS here being part of the LSMS acronym. Now, since the local chemical environment around each atom is included in the DFT calculation, this helps us treat each atom individually while retaining the randomness of their local chemical features. And not only that, but in establishing this radial cutoff, we can also rein in the overall demands of the calculation in a much more controllable manner. So the computational demands can, scale linearly, for example, with system size. So to emphasize, the LSMS can therefore provide us with a solution that not only respects the random statistical nature of the problem, but can also resolve local chemical features in the way that CPA cannot, as schematized, with the various shades of green, orange, and blue, etc., that we have here. All right. So now we have some motivation for studying the problem disorder, specifically for applications involving high-entropy alloys. And we've also introduced a couple of the modern techniques for first principles disorder modeling, including the effective medium CPA approach and the LSMS supercell method. With that, now we can start talking about the recent Must paper, where these two methods, among others, were compared in their performance for both high-entropy alloys and some conventional ones. So a lot was discussed in this paper, including some of the points we already mentioned when we introduced the effective medium CPA approach and the LSMS methods, right? But what I want to additionally focus on here are some of the LSMS supercell statistics and the linear QV relationships that the paper establishes for high-entropy alloys. But first, to generally understand what's going on here, let's take a step back and define a couple of things which are shown, like this Madelung potential, Vmad on the y-axis down here. Well, this Madelung potential is just the local electrostatic potential for a given atom in this crystal, say the blue one over here. And this is just computed by summing over the Coulomb contributions coming from the remaining atoms throughout the rest of the crystal. All right, now let's consider a periodically ordered solid for the moment. Then by definition, it has translationally equivalent sites, say the center yellows over here. And these all have the same configuration of atoms surrounding them. What that means is that, the Madelung potential is also equal between equivalent sites and is therefore periodic as well. And when this happens, the electrons that are influenced by this periodic potential can also arrange themselves in a similarly periodic manner. So now, if I consider the neutral atoms that I brought together to form this periodic solid, well, that means all the equivalent atoms will have seen the same number of electrons either leave or enter their orbitals once incorporated into the solid. And so this so-called charge transfer was actually the second concept that I wanted to establish for the x-axis of these plots, and for which I've done in the periodic case. But now for the disordered problem, the atomic environments are random now. And that means that I now have to have some statistics for both the Madelung fields and the charge transfer, right? Because even if I'm looking at a particular species, well, this green atom's environment is different than that green atom's environment. And therefore, they're going to see a different number of charges transferring and in different electrostatic Madelung fields, according to the underlying disorder in statistics. So now, going back to the results of the recent paper, we can see that the charge transfer statistics that were provided by LSMS for the high-entropy alloy over here, as well as for a more conventional binary alloy, which I copied to the right column over here. For comparison, we can also look at the CPA result for different elements that form the alloy, shown by the blue dots in this panel, and the red dots in that one. All right. Now, from these figures, we can see that the distributions are quite Gaussian in their shape. But in addition to this, by scatter plotting these charge transfer statistics against the Madelung fields, the paper also establishes jointly linear QV relationships between the two random quantities for each atomic species. So these arrows here are just connecting the average LSMS result across the two rows. So the black triangles on the blue dots on the left, right? And then something to add, however, is that with these QV relationships, the paper also showed it was possible to reincorporate some species-dependent corrections into CPA, and then have this new corrected CPA perform a bit more accurately, which we can get a sense of, by looking at how these red corrected CPA dots compare with the blue LSMS averages. One thing I also want to add is that, if we look at this bottom panel over here, we can see that CPA alone, the black crosses, right, they show a Madelung potential that's completely uniform. And this is due to some of the issues that we talked about earlier, where each atom in the CPA sees the same environment and therefore has the same electrostatic potential. So clearly, these corrections, these are quite significant and can improve the accuracy of CPA without sacrificing too much of its computational affordability. All right. So these are the main points that we wanted to review from the previous paper. That is, the Gaussian charge transfer statistics produced by the LSMS and the linear QV relationships, as well as the fact that these QV trends can then be used to make systematic corrections to CPA. And this last point, it'll serve as a little bit of a motivation for us to get to the heart of these statistics. All right. So from these results, we can further ask a few simple questions. Namely, what controls this supercell statistics for the charge transfer and the Madelung fields, as well as the joint statistical QV trends? All right. And is there a simpler way for us to describe and understand all these features? right? So I have the goal today is to outline these questions, or to answer these questions that I've just outlined. And for the remainder of today's talk, we're going to try to get to the heart of both the qualitative statistics by constructing a minimal working model that can recover the same features. And this will allow us, to try to work out some of these answers in greater detail in a simpler toy problem that can afford us deeper physical insight. All right, so the starting point of our theory is a simpler single band model, which provides a minimal working description of spinless fermions that are weakly correlated through electrostatic interactions. So these are occupying an n-site lattice with some moderate chemical disorder, and the Hamiltonian we use is given here. So I'll mention that, because our upcoming theory is a perturbative one, we've already taken the liberty of separating things out into a bare part plus some perturbation. So for the bare Hamiltonian, H0, we're using a nearest neighbor type binding model that is trivially diagonal in momentum K-space. And this captures the tunneling kinetics with hopping T and single band dispersion CK. All right. Now, both the chemical disorder and the electrostatic interactions are going to be treated as local perturbations to the bare problem. So we include these site energies, epsilon I, corresponding to the disordered background of impurities, while phi I here, it's an electrostatic Hartree mean field that sums over the Coulomb contributions from the remaining J not equal to I lattice sites. What I should point out, though, is that what I've just introduced as this Hartree mean field is exactly what I described as the Madelung field in the previous slide. Therefore, this phi I will precisely represent the V Madelung that we want to study. All right, so that covers the basic features of this disordered Hartree model. Now, how do we solve it? Well, like I said, we're approaching the problem perturbatively, so we can, develop our solution using the Dyson equation, which allows us to expand the full Green's function G of the full problem in terms of the bare Green's function G0 of the bare problem, together with the perturbations B. And from the Green's function, we can extract the electronic profile. That is the local charge density, Ni, in the full problem. And we can similarly express this in terms of the bare density and average of the bare type binding problem, which happens to be uniform for our solution of for our choice of H0 and coincides with the filling. Their difference, is then giving us the electronic charge correction resulting from perturbations, as we show here, expanded in terms of these epsilon tildes, where these epsilon tildes, these are just the eigenvalues of our potential operator. That is, they're the total on-site perturbation that sums the impurity epsilons together with the Madelung phi's. All right. Now, something I'll add is, this charge density correction, delta n, this can be associated with the charge transfer that we're interested in. And we also have it right here, expanded in terms of these Madelung potentials phi, which are contained inside these epsilon tildes. All right. And if you'll remember from the previous slide, we had said that we wanted to study the linear relationship between the charge transfer, delta n now, and the Madelung field phi. So what this tells us is that, we want to be in some linear charge transfer regime, and we therefore truncate our expansion just to first order in epsilon tildes, where the only remaining expansion coefficients have been defined here, and these depend only on the bare position Green's function, as well as the filling or the chemical potential mu. I also just wanted to point out that, we've chosen particularly to separate this expansion into a local on-site term with coefficient A and non-local contributions with coefficients Bij as separated here in the expansion. All right. So now we have an equation with our two variables of interest, delta n and phi. But if we look back at our Madelung definition for phi, well, we notice here that there's a delta n nested right in that sum over there. So that's a second equation with phi now as a function of delta n, right? So delta n is a function of phi. Phi is a function of delta n. This establishes a self-consistent pair of equations that we want to solve. And now, how is this done? Well, actually, in our linearized theory, we can solve these equations algebraically. We just need to kill off some of these sums by Fourier transforming over to momentum space, where we can apply the convolution theorem. Anyways, I won't drag you through all the algebra and transformations, at least not again, because we have gone through this through a previous talk, but it's been a while, so I copied the main result down here. And then if I go back to position space, what do I have? Well, I have a linear response theory for both the charge and the Madelung potentials, as a function or functional of these impurity energies epsilon. So that actually reveals to us that these m and m tilde coefficients that we introduced here, these are our linear response functions, and these can be computed, just using the expansion coefficients of our perturbation theory, A and B, together with the Coulomb potential profile, which, just depends on the displacements between lattices, or in other words, the crystal structure. All right, so I recognize that the last slide may have been kind of theory heavy. So just to see how different parts and things kind of work together, I thought it might be useful to maybe run through what an example calculation might look like in this disordered Hartree framework. So as a first step, we just parameterize the Baire problem to establish what things look like without any perturbation. So, I'll set like my lattice geometry, my filling, my hopping, and such, and all at this step. Once I set all that, I can compute the band dispersion, CK, with A here being the primitive vectors of the cubic lattice that I've chosen. So over here, I'm plotting this, CK over the first Brillouin zone of the cubic model with unit lattice spacing and unit hopping as we're setting over here. And then from this band dispersion, I can then compute, the Baire momentum Green's function, do a lattice Fourier transform, and then get the position space matrix elements, like I'm showing in these two plots for the real and imaginary parts. And these are all shown for a couple of choices of Rij, or the site separation between I and J. All right. Now the next step is usually to take the position Green's function that we just got, and then use them to compute the expansion coefficients A and B. So using our earlier definitions, we can compute the A and the Bij's for the same half-filled cubic model, and then also take this opportunity to Fourier transform B over the momentum space, plotted here just along one of the Cartesian axes in a K space, and over here just along some K path that actually hits all the high symmetry points in the cubic Brillouin zone. All right. Now in step 3, we're going to be constructing our linear response functions, m and m tilde. But what do we need for this? Well, I mentioned very quickly before, but what we need are the A and B K coefficients that we had just computed, sure. But what we also need is this momentum profile for V Coulomb. So for this, I won't get to too many details. But what I will say is that, the lattice transform of this 1 over R Coulomb potential, it's generally pretty hard to compute directly due to some convergence issues that you might run into when summing over all these long-range contributions. For this, though, we can use the standard Ewald summation technique, which kind of resums things a bit more efficiently, and then allows us to compute these momentum profiles as I did over here. From this, we can see that the potential starts to blow up as we approach near the origin. And this turns out to actually go like 1 over K squared, which is the usual behavior that we expect if we think about the Coulomb potential of a continuous Fourier transform, or the Coulomb potential's continuous Fourier transform in 3 dimensions. Right? However, what changes is in our discrete treatment is that this profile also now has to satisfy some periodic boundary conditions in momentum space, these being set by the crystal lattice structure itself. So basically, what this means is that the standard 1 over K squared dependence, it's going to get modified away from the origin, and then more drastically changes towards the edges of the corner of the Brillouin zone, where it has to satisfy these boundary conditions. Anyways, that's all I'll say about this part. But with this V Coulomb momentum profile at least, and our perturbative expansion coefficients, well, then we can construct the MK and the M tilde K profiles like we do in these two plots. And then basically with these, we're just a Fourier transform away from our final step, which is usually to start running simulation cells for different instances of disorder. Because once we have these, M and M tilde matrix elements in position space, then it's just a matter of inputting a bunch of random site energies, epsilon, and then applying our disordered Hartree equations to get the charge correction and Madelung field distributions throughout the crystal. All right, so this basically covers what a generic procedure might look like in this disordered Hartree framework, and then shows how, the different ingredients of our theory all come together to form a solution. All right. So all this has been, pretty technical though. So let's now consider some simpler applications of our theory, where some of the more basic physics it contains can be made more clear. So first we'll be looking at the non-interacting limit, where we don't have to worry about the electrostatic Madelung field phi anymore, or the associated m tilde response functions. Now, if we consider just a single impurity epsilon sitting on site J, well, the charge correction for site I is just going to be given by this form, where I've just removed the sum over J compared to the previous slide, because we only have one impurity to care about. And where Mij is just given by our expansion coefficients, at least in this non-interacting limit. Now we can plot these below as we vary both the position and the strength of the impurity while fixing site I to the origin. And then from these curves, we can see that the density corrections oscillate and decay away from the impurity. Right? So these are actually analogous to the so-called Friedel oscillations that are generated around a single impurity in an ideal Fermi gas. And in this related problem, the density corrections usually oscillate at twice the Fermi wave vector while decaying as an inverse cube. All right, so now we have these Friedel oscillations in the single impurity example, but the generalization to many impurities is pretty straightforward. Each impurity defect, therefore, is generating its own Friedel oscillations, and these effects are additive in our theory, since we're just restoring the sum over J in order to add up all their contributions and build the local charge correction. All right. So what happens now when we start turning interactions back on? If we do that, then a lone impurity at site J is going to induce an electrostatic Madelung potential on site I of this form, where we just have the general Fourier expansion of m tilde ij here, this inner element being m tilde k. All right. Now, if we again take the impurity and start moving it around the lattice a little bit, well, we can see how this m tilde ij behaves. And we'll notice that, at far enough distances away from the impurity, the log of the Madelung response, it falls off and can do so pretty linearly in some limits, like we've shown in this example calculation here. Now, why this result is important to us is it revealed actually electrostatic screening in the Madelung response, presumably of this form, where we have some exponential envelope set by some screening length L, and another probably weaker function of distance, f of rij. And this is all reminiscent of Yukawa screening, where f would just go to some inverse distance, right? And of course, just as before, if we're to consider multiple impurities now, well, our theory is additive, so we just extend things by restoring the sum over J, and then add up all the screen potential contributions into the local Madelung field. All right, so that basically covers all the core aspects of our theory that we can understand at the single impurity level. And just to rehash, we saw that we have Friedel oscillations that are generated by the impurities and superimposed to form the local charge correction, at least in the non-interacting limit. And we also saw that when we turn interactions back on, well, these impurities also produce electrostatic potentials that are screened and then combined to form this Madelung field in the crystal. So with that, let's now actually look at some of this physics in action when we have multiple impurities. All right. So now we're going to have a full realization disorder. Though the simplest example for us to deal with is probably the case of binary disorder, where we constrain each impurity epsilon to be either one of two equal and opposite values with equal probability. So say plus or minus 1. And running through a million or so of these disorder configurations, we can collect all the relevant disordered Hartree statistics for the same cubic model, right? So this will include the local charge correction, delta n for site I at the origin, as well as those of the local Madelung fields. And these are all color-coded, according to impurity type. So red would be the positive species, and blue would be the negative species. Next, what we can do is we can combine these two histograms in the middle over here, and then plot the joint phi I delta ni statistics over here to the right. This can be done both at quarter filling and at half filling these two rows. And by comparing these, well, we notice that the statistics look pretty Gaussian in this quarter filled example as compared to the bottom. And what we found actually is the cause of this difference is apparently due to the different screening efficiencies that occur at different fillings. All right, so this can be understood in the following manner. First, we can recall our disordered Hartree relationships, which represent delta n and phi in terms of their linear response functions. All right, so now let's consider an example where things are only weakly screened. In this case, impurities farther away from me can have more of an influence on me locally and make sizable contributions to my sums here. So if I'm summing more and more random terms, at some point the central limit theorem is going to kick in and produce the Gaussian statistics that we see in this more weakly screened regime, represented here for us by the quarter-filled case. Now, at half-filling, when the screening is sufficiently strong, this means that only the nearest neighboring sites are going to be affecting me and contributing to my sums. In this case, the disordered Hartree statistics can develop some more non-trivial features, like these spikes and these horns that we have over here. And these, presumably have some additional dependence on model details, like crystal geometry or the disorder profile of impurities, etc. All right. So now, calling back to the recent Musk paper that we discussed several slides back, I just wanted to remind everyone, that one of the things that we wanted to capture from the LSMS supercell results were those Gaussian charge transfer statistics. And so from our calculations, we find that the disordered Hartree theory does reproduce this, at least in the weaker screened regimes for the reasons that we just discussed. In addition to this, though, we can see that, even at half filling, while not perfectly Gaussian, there does seem to be some, Gaussian envelope on the statistics here. All right, so that's all good to know. And in addition to this, what we also wanted to recover were those linear QV curves for the joint charge transfer and Madelung field statistics. Well, if we look at our analogous phi I delta Ni joint statistics, we see that this is reproduced in our theory pretty well. And, so part of the job is done. We have a simple theory that reproduces the right qualitative statistics that we want to study. Now, the remainder of the talk can be dedicated towards, determining what governs these statistics and how we can develop a simple way to describe some of their basic features. All right, so let's try to analyze the statistics that we've just established and understand things a bit more carefully. So first, we'll define this ensemble average over disordered configurations, just using a double-angled braces for the corresponding expectation values. All right. Now we'll be considering impurity statistics that are locally conserving, where the epsilon site energies, disorder average to 0 for any site J in the lattice. And we'll also stipulate that the disorder is truly random, such that the intersite correlator is diagonal, right? So this just means that, the impurity statistics of different sites, J and J prime, they're strictly independent from one another. And we're also using this W as our general measure of disorder strength. Now, I just want to point out that I haven't really said any more particular details regarding the underlying impurity statistics. All I'm telling you is, what these expectation values are. Therefore, what we're about to run through should be pretty general and hold for, an unspecified distribution of impurities as long as they satisfy these general conditions. So this will also actually include the binary problem that we simulated earlier, where each epsilon J would then assume equally probable values of either plus or minus W. So this general formalism will be useful to us either way. Right. All right. So now, having established this form for our impurity statistics, we can see how these carry through our disordered Hartree calculations and then affect the statistics of the charge correction and the Madelung fields. So first, if I take these identities and just sandwich them, within the disorder average, well, as I saw before, the M and M tilde response functions, those both only depend on the intrinsic model parameters without any regard for statistics. As such, they can persist despite the disorder average, and they're ignored by the expectation values. So that just leaves us, with these averages over epsilon J, which our first condition can kill off the result for. All right. I can compute the mean squares next in a similar manner, where this time, our second condition is going to apply to the intersite correlators nested inside the double sums. And well, because the averages for either quantity was 0, this means that, the mean square is also equal to the variances by the usual definition, because the second terms are just a 0, right? All right, so we computed a bunch of things, including the averages and variances. But so far, we've only been talking about the overall statistics without any regard or distinction for chemical species. So basically, all we can determine at this level right now is the total statistics are centered at 0, and that we have some measure of the spread of the variance of the overall distribution. But if we want to resolve the disordered Hartree statistics a bit more, well, we're going to have to dig a bit deeper and start looking at subsets of these overall statistics, which can help us discriminate between different chemical species. All right, so separating things out by species now, we're going to have to define this new species resolved average, where out of all disorder instances, we're only keeping the ones where site I has an impurity of species alpha sitting there. All right. Now, what do our impurity statistics look like? Well, if we consider the species resolved average, this can only be non-zero if the site I'm constraining to species alpha is the same as the site that I'm averaging for, J in this case, right? Because if I'm constraining site I to be some species alpha, and then I ask you, what are the statistics doing over there at some different site J? What can you tell me? You can't tell me anything special, right? Because while I'm sitting here constraining site I, site J can take on whatever impurity it wants. And we already established in the last slide that this unconstrained average should be zero, hence the delta function. So now when site I equals J, we're just, we know that each sample of our species resolved data set is going to have the same kind of impurity, which we'll just denote with that epsilon alpha. For the intersite correlator, what I'll mention is that, resolving the local statistics by species isn't really going to have any effect on how two arbitrary sites J and J prime are correlated in general. So, the second condition doesn't really look any different than from the unconstrained case. All right, so just like we did before, I can take our disordered Hartree equations, but this time I'm going to be separating out the local components, all right? And now, when we compute our species resolved averages, well, I can see that with the first condition, only the local portion is going to be able to survive. This just leaves us, with an on-site response and the impurity energy, epsilon alpha for us right now. Now for the mean squares, like I said, our second condition hasn't really changed. So we get the same result that we had in the previous slide for the overall statistics. And the variances are then computed in the usual manner. One last thing I'll add is that, we can also compute now the covariance between delta n and phi using the usual definition, where we now have some, product between m and m tilde nested inside the sum, rather than just having either one of them alone, right? Or, yeah. Anyways, these are the basic statistical properties that we can discern at the species resolved level, where the mean and the variances, give us the position and the spread of each of these groups of data points. Now for the covariance, we'll remember that statistically speaking, the covariance tells us about the correlationship between delta n and phi, basically how strongly they increase or decrease together or against one another. So as it turns out, this will be pretty useful in describing the line which best fits the species resolved statistics. And in the next slide, we'll actually talk about how that can be computed in our disordered Hartree framework. All right. Now, how do I compute these lines of best fit? Well, what we have to do is we have to minimize the mean squared error of our data points from some line, call it m phi plus b, right? Just to let you all know, we're indexing everything with alpha, just so that we can resolve things by species and have a different line for the positive and negative species in this binary case. So the two optimization conditions are shown here, and we have two conditions, two unknowns, and we can solve this linear pair of equations in the following manner. I'm skipping all the algebra, but just want to point out that these fit parameters, these will end up being expressed in terms of the disordered Hartree moments, which we actually computed on the previous slide. Therefore, those identities that we obtained can be used to re-express things in terms of our m and m tilde response functions. So, just looking at the binary problem where epsilon alpha is either plus or minus w, we can see that things simplify a bit, and that the slopes of either one of our species are going to be the same, while the y-intercepts are going to be equal and opposite as a result of the signed result over here. All right, so this is how we can determine what the best fit line is, and how these will correspond to the linear QV trends from the Must paper that we're after. Now, for more on these joint statistics, well, we can consider the underlying probability distribution that produces them. So converting those scatter plots to heat maps now, we notice that they have these isoline features that look pretty elliptical, for both the quarter and the half-filled problem we've been looking at. Okay. And now if we plot this as a 2D histogram, we can see that the joint probability distribution in delta n and phi, well, these have been normalized to 2, one for each species. All right. These look pretty Gaussian, especially in the top example. And from our earlier disordered Hartree histograms, which we can actually get by integrating out either one of these axes and then rescaling things to go from probability distributions to occurrences, right? This all shows us that, we have some ellipsoidal isomorphic features, some Gaussian looking statistics. So with all this information, we can use, some intuition and apply a standard approximation for the joint probability using this 2D generalization of the Gaussian. So this so-called bivariate normal distribution is entirely parameterized in terms of the disordered Hartree moments that we computed for the species resolved statistics in the previous slide. Just to be clear, I'm replacing phi and delta n with x and y now, just to reduce some of the notation down. And mu x will correspond to mean of the x, and sigma x squared will correspond to the variance. While inside of this row, we have both sigma x, sigma y, as well as sigma xy, which is the covariance that we computed as well in the previous slide. All right, so just to see how this compares with the real data, we can then pull the tops off of each of the bins of the histogram, scatter plot the same data, which are now separated by species. Negative, positive. And then we can compare these against the bivariate normal distribution that we have presented up here, which are shown also by these green surface plots, and the arguments are obtained using the disordered Hartree moments that we computed in terms of m and m tilde. Right. So from this, we can see that things work out pretty well for the quarter filled case. However, at half filling, it's not really built to, at least our bivariate normal distribution isn't really built to get all those little horns and features that we saw earlier. However, it captures the Gaussian envelopes pretty well, and everything looks to be on the right order of magnitude. So we can take that as a win. All right. So the last thing we're going to do today is determine the width of our species resolved statistics. That is the spread or the variance along the minor axes of our ellipses. So how can we compute this? Well, one idea is to define an operator that rotates our disordered Hartree statistics about their means, right? So that their lines of best fit become horizontal. We can then compute the new variances along the delta n axis in the rotated frame, right? So down here, I've got an operator, capital R, that does just that. And for any given species, this R is only going to depend on the slope corresponding to its associated QV line. And just to mention, we're keeping x and y instead of phi and delta n, again, just to keep our formula simpler, and the same for the prime counterparts over here. All right. So anyways, applying this operator, to all the data points that we have at least, this will rotate our phi and delta n's to some phi prime and delta n prime. And from this transformation, at least on paper, we can also express the prime variables in terms of the original ones, and then start sandwiching things between expectation values, to compute the variances like we did in the previous slides when we were computing disordered Hartree moments. So I'll spare you guys all the algebra and just jump to the final result. Right. So these are the variances along either primed axes. So yeah, x prime would correspond to the phi prime axis, and then y prime would correspond to the delta n prime axis. Just to be clear. Okay. All right. So that's basically the end of our talk. But just to summarize things for everybody, today we developed a minimal working model of weakly correlated fermions on a lattice with moderate impurity disorder, and then used standard perturbative methods to construct a self-consistent screening theory within a linear response framework. We saw that our theory, was capable of reproducing some of the basic qualitative statistics that are seen in the LSMS supercell calculation from the previous Muss paper, and these included, the Gaussian charge transfer statistics as well as the Madelung field statistics, and then a jointly linear statistical relationship between these two random quantities. We then investigated these joint statistics a bit more carefully, and then figured out how to describe, the statistical moments like the means, covariances, variances, and such in terms of our m and m tilde response functions. We also figured out how to, determine the line of best fit, as well as the statistical spread about the line, using the same language with m and m tilde. Finally, we came up with an approximate description of the joint probability distribution in the phase space spanned by delta n and phi. And we saw that this worked pretty well, especially in the weak screening regime. right? Where the statistics are more Gaussian. So with that, we've basically got a pretty complete description of the statistics. We've got a pretty complete description of the statistics within this disordered Hartree framework, where we found that everything can basically be tied back to our linear response functions, m and m tilde, right? And now, for the last point, right, for some possible research direction, it might be good to extend these results and then see how well they hold up in real materials when treated more rigorously from first principles. And this is something that must maybe be able to contribute to the story. For instance, maybe we can try constructing these response functions using the Musk codes, and then using them to determine to reproduce those QV trend lines and such. And if things work out pretty well, this will also kind of open up an avenue to add systematic CPA corrections, like was done in the previous Musk paper, but maybe in a more practical manner, since the QV trend lines would be produced using our simpler linear response formulation, rather than running through all the LSMS calculations every time. So with that, I thank you all for your attention and conclude my talk. I can take any questions.
Thank you very much, Dave.